Okay. So, um, I continue from where we ended up last week. Let me remind you that we considered the Poisson neuron. So we considered we started to consider examples for the Fisher information in the activity, in neural activity. So we discussed a single Poisson neuron. We imagined that the average of the number of spikes emitted by the neuron is some function of theta. Okay? And this is a Poisson process. So this is a Poisson process. So if I specify the mean of the Poisson process, I specify everything there is to say about it. And remember that the Poisson process, when the mean of n is large, it kind of looks like it's a discrete process. P of n is discrete, but when n is large, it looks more or less like a Gaussian. When it's small, it's a Bernoulli process. And we calculated the Fisher information, and this is what we got. And several things to note about this expression, several simple things. There's one, that it has the correct units. F itself, in this case, is dimensionless because n is a number. But f prime is a derivative with respect to theta, so it has dimensions of 1 over theta, and it's squared. So we have dimensions of 1 over theta square. 1 over the dimension of theta square, and that's what we expect for Fisher information. Another simple aspect of this expression to note is that it vanishes if f prime of theta is 0, which makes sense. If the response of the neuron is independent locally on theta, it makes sense that the Fisher information is sensitive. We can not use the activity of the neuron to discriminate between small changes in theta. And another simple property which is useful to note is that if we multiply f by a factor, we make the expected number of spikes of a neuron larger by a factor alpha. What happens to the Fisher information? This you don't see? Okay. So if f goes to alpha f, what happens to the Fisher information? It's also also multiplied by alpha. We have a factor of alpha square here, factor of alpha here. So j goes to alpha j. So neuron that fires twice as many spikes has double the Fisher information. I'll talk about the interpretation of this in a slightly different context in a moment. And the next example that I want to talk about is a Poisson process. Okay? Mhm. Yes, the variance of any estimator. So, so the variance of a hmm? No. What the, if the Fisher information goes to if f prime goes to zero, if f prime is zero, it means that small changes in theta don't affect the firing rate of the neuron. So it makes sense that we cannot use the activity of the neuron to identify very small changes in theta. Okay? So now based on but now what the Kramer-Rao bound tells us is that if we try to construct an unbiased estimator of theta, it's important. If we try to generate an unbiased estimator of theta, it will be useless in this case because its variance will be infinite. Very often, we can generate a good biased estimator. Why? Because even if the neural response, okay, suppose that theta is over some finite range, and this is the possible range of theta, and this is a particular theta at which we're trying to do the estimation. For example, so because the range of theta is finite, we can construct an estimator which will always give an answer, say, of that particular theta. Okay, it will not be it will be a biased estimator, but it will have a finite variance because theta, the real true theta, has a limited range. But the biased estimator will have an infinite variance. Okay. Okay, so now I discuss a Poisson process, and what is the difference between a Poisson process and a simple Poisson variable? So let's define a Poisson process. Poisson's process is a function of time. It's what is called a point process. It's a set of discrete events. It's a point process. Think of these events as spikes. So a neuron generates spikes, and the question is, what is its probability to generate a certain spike train? For a Poisson process, the probability distribution has a very simple structure. Within any infinitesimal time interval, between t and t plus dt, the probability for a spike is equal to lambda times dt, and the probability for no spike is 1 minus lambda times dt. And lambda is the rate of the process. If we're talking about neurons, it's the firing rate. The other important property of the defining property of the Poisson process is that this is independent in different time windows or time intervals. So the probability of the Poisson process to emit a spike, to emit an event at some particular t, this time interval is completely independent than its probability to emit a spike in another time interval. And it turns out that if we look at the number of spikes within a finite time window, okay, so this is for an infinitesimal time interval. In an infinitesimally small time interval, the process will either emit one spike or emit 0 spikes. If we look at a finite interval, delta t, the number of spikes emitted within that interval, first of all, will be completely independent of the number of spikes in another non-overlapping interval. And within the interval, it will be distributed as a Poisson process. I'm not proving it now. Not a Poisson process, but a Poisson distribution. With mean, what will be the mean? The firing rate times delta t. Okay, how do we? This is easy to prove that this is the mean, because we can divide our finite time window into many infinitesimal small time windows. In each one of them, the mean of the number of spikes is lambda times dt. We need to do an integral over dt within the interval of length delta t, so we will get lambda delta t. So this is easy to prove. To prove that it's a Poisson distribution is a little bit more complicated. We will not do it now. And so now, this is a defining. This is a definition of a Poisson process. And what we want to do now is to consider a neuron with firing rate which emitting spikes as a Poisson process. With rate lambda, which depends on a parameter, theta. Okay? And now suppose that what I observe the spike train within an interval delta t. Okay, t. Let's without loss of generality, let's assume that it's an interval of times t going from 0 to delta t. Okay. So what does it mean that I observe the spike train? It means that I observe the timing of each particular spike. So in each realization of the process, I will give you a list of times t1, t2, up to tn. This list might be empty if there was no spike within the interval. It might have one spike, it might have two spikes. But in any instantiation, I will tell you what was the timing of all the spikes emitted by this neuron. And my question is, what is the Fisher information in this random variable, in this random process? What is the Fisher information about theta? Okay. Yes, for just a moment.
So we assume that in the
Infinitesimal?
it's independent.
Yes.
And then we do the same for the discrete time
Yes,
interval.
it's finite.
But can we get this without this? Because I think
for the mean, we didn't need the independence, because the mean of a sum of variables is always the sum of the means, regardless of whether you are adding up independent or independent variables. But in order to conclude that it's a Poisson distributed as a Poisson process, you do need to use the independence.
But can it be independent in a discrete interval and not in the...
In principle, you can define such a process, which is, in some divide time into finite intervals and consider a process that is completely independent in these finite intervals. But that's a more complicated construct. We're not discussing it right now.
Okay.
So the Poisson process, what if... Yeah.
Biologically, this sounds plausible, but it's...
Okay, biologically, it's a little bit too crude to just decide that you divide time into, very well-defined intervals and you say it's independent here from here. It's true that it makes sense that the spiking of a neuron over, any neuron at this time is is largely independent of what it did far away from that time. That's true. But
we know that for very small intervals, they are very independent.
That's a very good point. That real neurons have refractoriness. They cannot spike. If they emitted a spike now, they will not emit a spike in the next few milliseconds. So this means that the approximation of a Poisson process is not a good approximation for neurons that fire at a very high rate, because then, at least over some time scale, it's not independent. For neurons that fire, say, cortical neuron that fires one spike every second, it doesn't really matter that much that there is this interval. But this is a good time to say that the reason we're talking about the Poisson process is that it seems to be a good approximation for the statistics of firing of, at least as a crude approximation for the statistics of firing of neurons in the cortex. So very often, if you look at the statistics of firing of a neuron in the cortex, I will not go into detail on this, but it will roughly look similar to a Poisson process. There are various properties of the Poisson process that you can observe on any time interval, so except for very small time intervals due to the refractoriness. So for example, if you look at the variance of the number of spikes emitted in a certain interval, it will be of the same order of magnitude as the mean. This is a property of the Poisson process. If you look at the distribution of the interspike intervals in a Poisson process, this distribution is exponential. And this is a rough approximation for what is observed in the cortex. Of course, it's not precise. And it's also a very interesting question to ask, why would the neurons in the cortex fire as Poisson processes? Intrinsically, we have models for what a neuron does, crude models like integrate and fire neuron, or more complicated models like Hodgkin-Huxley. This is not a Poisson generating process. So why would neurons in the cortex fire as Poisson process? It's an interesting question. I'm not discussing it here. But this is our assumption right now. Okay? So so the theoretical game that we're playing is the following. We have a neuron that's generating a Poisson process. I allow you to observe the spikes, the precise timing of all the spikes that this neuron emitted in a time interval delta t, and I ask what is the feature information in this observation about delta theta. So this seems like a complicated task, because we need to consider the probability distribution of all possible spike trains, right? It's very different from what we did when we considered the Poisson variable, which emitted one number. Its output was just described by one number, the number of spikes. Here, it's a list of numbers which can have varying lengths. The neuron may have emitted 0 spikes, 1 spike, 2 spikes, and I give you the precise timing of each spike. Nevertheless, it turns out that for a Poisson process, the answer is very simple. And this is because if you ask what is the likelihood of a particular observation, T1, T2, Tn, remember, this can be empty. No spikes, so the observation is both the number of spikes and their timing. If you ask what is the likelihood of this given theta, for a Poisson process, you can show, I will not do it right now, that this really depends only on n. There is nothing to learn about theta beyond. If I tell you what is the number of spikes that the neuron has emitted within this time interval, you will learn nothing further about theta by knowing what was the precise timing of the spikes. Okay? This is a very non-trivial statement. For most point processes, it's not true. If I will just tell you how many spikes occurred for a general point process, this will be less information about the parameter than if I tell you what was the precise timing of the spikes. For a Poisson process, it's related to the fact that the timing of the spikes is completely independent in different intervals. If I tell you how many spikes occurred, you can learn, this allows you to learn everything that you might hope to learn about theta. And the term in statistics for such a situation is called sufficient statistics. N is a sufficient statistic for the more full description of the statistics, for the full distribution. Okay, again, I'm not proving it right now. We will do this either in the TA session or in a home exercise. But once I tell you this, the problem becomes very simple, because as I've just mentioned here, n is distributed as a Poisson distribution, right? N has a Poisson distribution with mean delta t times lambda of theta. And we know what is the Fisher information in a Poisson distribution that depends on a parameter. So J is equal to, remember, we have to take, when we wrote it as f of theta, we had f prime of theta squared divided by f of theta. And so what we'll get here is delta t times lambda prime of theta squared divided by lambda of theta. And the linear dependence in delta t is the outcome of the same property that I discussed earlier for the Poisson distribution, that if f is proportional to some prefactor, then the prefactor enters linearly here. Does everyone see this? No. No. Okay. Okay. So it's f prime squared divided by f, which is also equal to delta t times lambda prime squared divided by lambda. Okay, so right now we're not even thinking about other delta t's. We're thinking of one particular interval of length delta t, and I'm asking what is the Fisher information conveyed by the spiking activity about theta. Now, we could have decided from the start to imagine a situation where all I'm telling you was the number of spikes. Then it would be then we could immediately say that this is a Fisher information, because the number of spikes is distributed as a Poisson distribution. But what I discussed previously about the sufficient statistics implies that it's even beyond that. Even if I tell you what was the precise timing of all the spikes, it doesn't give you any further information than knowing the number of spikes, because it's a Poisson process. Yes.
And then say what is
Yes.
Fisher information, and from the beginning you said that the process is Poisson distribution of mean. I mean, did we need a sufficient
So again,
argument about it?
yes. So if the situation would be a situation where all I tell you is how many spikes the neuron emitted, I don't reveal to you at what times the spikes were emitted, we would not need the sufficient statistics property, because the number of spikes, it's one number. It's distributed as a Poisson distribution with this mean, and we know what is the Fisher information in a variable that has a Poisson distribution. But I'm saying something else. I'm not telling you how many spikes the neuron fired. I'm telling you more than that. I'm telling you at which specific times the neuron fired. So it's not obvious that Fisher information would be the same thing. Maybe the precise timing provides you with more information about theta. It turns out that because of the independence in different time bins, we have this property of sufficient statistics that the probability of the whole spike chain given theta is only a function of the number of spikes, and therefore we get this result. Okay, essentially, again, knowing the precise number of spikes in a Poisson process does not give you additional information than just the total number. Okay, so several comments. Sufficient statistics we discussed. Okay, why is J proportional to delta T. I claim that in the context of the Poisson process, we can understand this intuitively based on what we know about Fisher information. Does anyone have a suggestion why it's proportional to delta T? So I'll help you a little bit. Remember that Fisher information of two independent variables is the sum of the Fisher information in each one of them. Does this help?
Proportional to the number of possible spikes.
Okay, okay, that's a somewhat vague explanation. Okay, so we can always divide an interval into subintervals. So the Fisher information of delta T, we can think about, so it's based on the number of spikes emitted at the interval of length delta T, but we can decide to divide this interval into two intervals of length delta T over 2. We know that the number of spikes emitted here is independent of the number of spikes emitted here. So this has to be equal to J of delta T over 2 plus J of delta T over 2. Or in other words, twice J delta T over 2. Right? And the function that has this property, the only function that has this property is a linear function.
But this is J of delta T, not of theta.
Okay, sorry. So this is just the notation that I'm using is a bit confusing. J is a function of theta, but let's think
J
about
given delta T.
J for theta for an observation of length delta T. Okay, so let me write this again. Here I mean that this is a parameter, okay? So this will be J of theta delta T over 2 plus, I'll already write it as twice J of theta delta T over 2, and this implies that J is linear in delta T. Okay? This is because of the independence. The Fisher information in a longer time interval is just the sum of the Fisher information in subintervals because of the independence. Now, another comment. Is that based on the same arguments, if we go to a very large delta T, we can think of our observation as as a combination of many independent observations. The number of spikes which we observe over an interval, over a longer interval delta T, can be thought of as the sum of the number of spikes in many independent intervals. And therefore, all the properties that we mentioned earlier that are valid in the limit where we have a sum over many independent variables are valid. So in the limit of large delta T, the maximum likelihood estimator achieves the Cramer-Rao bound. And the discriminability is directly related to the Fisher information. Okay? Remember, in both cases, we assumed, we proved these relationships in the case where we have a large number of independent observations. For sufficiently large delta T, a Poisson process can be thought of as that way, and therefore this property exists. Third comment that I'd like to make, right now I'll make it briefly. Consider a neuron whose firing weight depends on theta in the following way. It's 0 up to some point, and then it's construct this, that this function has such a form that the derivative here is not zero. Okay? From when you approach this, say, when you approach this point, the derivative does not approach zero. It's not, the derivative is not smooth. Okay? In that case, if you look at this expression, you see that as we approach, so let's call this point theta star, when when theta approaches theta star from below, you see that lambda prime approaches some constant, but lambda goes to zero, so the Fisher information diverges. Okay, so this is kind of interesting. It's you might wonder whether this means that we can have infinite discriminability or zero variance of an estimator. Doesn't really make sense that we can have a zero variance of an estimator, because if theta is slightly to the right of theta star, actually this neural activity tells us nothing about theta, right? So there's
Where is it from? This was a plot? I didn't understand.
I just imagine that I have a neuron whose firing rate looks, as a function of theta, looks like this.
Okay.
So mathematically, everything is fine. The Fisher information diverges as we approach this point. Okay, what does this mean? So it turns out, I will discuss this more later, but it turns out that, remember that the Kramer-Rao bound is just a bound. Okay? It's not true that you have infinite variance of an estimator. It's not true that you have infinite discriminability. In fact, in this particular case, in contrast to what I've written here, no matter how large delta t is, we're not in a situation where we can think of the observation where the proof of these two properties is valid. And the reason is that the spikes, that the firing rate of the neuron here is zero, approaches zero. So the probability to observe the spike as theta approaches theta zero goes to zero. I will discuss this in more detail in a slightly different context later. But what I want to tell you already now is that there are cases like this. I mean, it's not uncommon to have a neuron whose firing rate is zero over some range, and it's not uncommon to have a tuning curve, empirical tuning curve, that approaches zero with not smoothly. And so it might seem like the Fisher information diverges. It's true that the Fisher information diverges, but it doesn't imply that the variance of an estimator is zero, or that the discriminability is infinite. Okay. Next example that, but I'll discuss this further later. So next example that I want to mention.
Yoav, I think I didn't understand. Did we understand the thing over there from the delta t explanation, or the last delta t?
Well, the point is that when when it's large delta t, first of all, you can think about the observation as the sum of many independent observations, because you can divide your delta t interval into sub-intervals.
Yeah, okay.
And this was part of what we needed to prove that a maximum likelihood. When we proved that under some conditions, the maximum likelihood estimator achieves the Kramer-Rao bound, we used the assumption that it's the sum over many independent variables.
Only that?
Well, there are some other assumptions in there, and in fact these assumptions fail in this particular case. Other assumptions. I don't want to go into the details, but you can think about. It's an interesting question to think about. To look at the proof and try to think where things might fail. But essentially, I'll remind you that what we really did is that we showed that the log likelihood approaches a Gaussian variable. Okay. All right. Next example, very simple generalization of what I've written so far. Nothing much to say here. example, imagine that we have a population of independent Poisson neurons. So the expected number of spikes emitted by neuron I is its firing rate times delta t, and we observe the spikes over a time interval delta t. Then the Fisher information, because the neurons are independent, the Fisher information is the sum of the Fisher information from each neuron. So it's sum of I fi prime of theta square divided by fi of theta, or delta t times sum over I lambda I prime of theta square divided by lambda I of theta. Next example. I'll write the title, then I will explain it. Translation and invariant and dense receptive fields. What I mean by this is that I have some variable theta, and let's imagine just that theta goes from 0 to L. And if I look at one particular neuron, its Poisson process with a rate um, which I write as follows. You know what, I will write this in terms of the f, the expected number of spikes. Not to carry over the delta t factors all the time. So fi of theta is some function of theta minus theta I. Theta I is what we would call the center of the receptive field of this neuron. This neuron is maximally fires at the maximal rate when theta is equal to theta I. Right? And if I look at another neuron, each neuron has a different center of the receptive field. Okay, so we have a large set of neurons with receptive fields at every possible the positions. Well, maybe not every possible positions, maybe it's discrete, so the neurons have receptive fields, centers of receptive fields which are uniformly distributed. I will call this difference delta theta. Note that delta theta is equal to L over N, where N is the number of neurons. And I assume that this delta theta is small. You will see in a moment where we will need it. Small compared to what? Compared to the characteristic scale of this receptive field. So this is what I mean when I'm saying that the neurons are dense. The shift in the receptive field of different neurons is small compared to the structure of the receptive field itself. Okay, so now let's ask what is the Fisher information. J is the sum over I do with the sum? Hmm? No. Okay, the sum theta I is a theta I is a variable that goes through discrete values which are all close to each other, right? It's just discrete steps. So how can we approximate the sum? Hmm? So this is sum over. So let's call theta I times delta theta. So we have here sum over I f prime of theta minus I delta theta squared divided by f of theta minus I delta theta. And I already heard someone say that this is a what's this? Integral? Right? So we can approximate the sum as an integral. So let's write this as 1 over delta theta times sum over I and multiplied by delta theta here. Right? And now this sum is an approximation. When delta theta becomes very small, it can be replaced by an integral. One over delta theta, integral d theta tilde, f prime of theta minus theta tilde divided by f of theta minus theta tilde. This is squared, d theta tilde. But in fact, let's just shift our variable theta tilde and rewrite this as integral d theta, integral 1 over delta theta, integral d theta, f prime of theta squared divided by f of theta. And what is the range of the integral? The range of we neglect edge effects here. We assume that for most of the neurons, the receptive field decays to zero strongly enough that the tail beyond the edge of this range is not important. So then we can just write this integral as if theta is going from minus infinity to infinity. Right? So f of theta in our case looks like this. This is f of theta. This is theta. And we need to evaluate this integral. One very important property to consider is that, remember, delta theta was the range of the variable divided by the number of neurons. So this is n divided by L, integral d theta, f prime of theta squared divided by f of theta.
Why is from minus infinity to
Hmm?
why is theta is from minus infinity to infinity only?
Well, again, because in principle, for each neuron, we would need to set up, so for this particular neuron, we would need to set the range of integration such that we go from this point up to here. But I assume that receptive field decays to zero strongly enough that we can extend the range of integration to infinity and ignore the fact that theta was actually over a finite range. Okay? And it's not a precise assumption for those neurons whose receptive field is very close to the edge, but I will ignore this effect. Okay? Now, the most important thing to consider here is that if I throw more and more neurons into my population, while still obeying the structure of the receptive field, the Fisher information increases linearly with the number of neurons. Okay?
I don't understand your answer to today. I understand that I goes between increase maximum value can be L, the difference between two different theta.
So, okay, it's a bit confusing. So suppose that this is theta. Then theta I minus theta goes from this minus this quantity to plus this quantity, right? But what I'm saying is that for almost all the neurons in this range, I mean that the neurons with a theta I here are already okay. This is theta. The neurons with a theta I over here have a zero fine weight here anyway. Okay, so if I would imagine that there are additional neurons going all the way to infinity and to minus infinity, although there aren't neurons like that, it wouldn't change anything if I would add them because their fine weight decay sufficiently fast. So this is the justification for replacing the range of integration to be from minus infinity to infinity.
So it's an assumption you have about f.
Yes, so there is an assumption here about f, that f decays sufficiently fast beyond this, over a range which is much smaller than n.
But how does it help you to calculate?
It just means that I can replace this limit of integration by minus infinity to infinity, and it makes things simple.
So, can you explain when you moved from theta minus theta wave to 1 theta?
Yeah, I will just call theta minus theta wave wave. Okay.
Yeah, but the f tag of theta is not the real theta. It's just an auxiliary variable here. Where you substitute theta minus.
Yeah, but the derivative, it's a linear function, so the derivative with respect to this quantity is the same as the derivative with respect to the theta. I mean,
I'm just trying to understand if you change the variable,
yes.
or you're saying that
I'm changing the variable. So let's call this thing theta minus theta wave theta hat.
Okay.
Okay. So what do we need to write here? We have here f prime with respect to theta hat. So there will be a minus sign because theta hat is minus theta. I mean, there's a minus sign. Our summation variable. The integration variable is theta wave, so there's a minus sign, but the minus sign I don't care about it because there's a square here. And I need to evaluate f prime at the position theta minus theta wave, which is theta hat. So I will have here f prime of theta hat, and here I will have f of theta hat.
Yeah.
So
that's theta hat what you have there on the next line.
Yeah, this is theta. I already rewrote it.
So it's not the theta that we have there. That's what I was saying.
Good, very good, good point. Thank you. Okay, so let's write. I mean, let's just to be precise, write it as theta hat, and it's a good point also that this Fisher information, you see, it's independent of theta, which makes sense. When will it not be dependent? Where will it depend a little bit on theta? When we approach the edge, because when we approach the edge, we will have more neurons on this side responding. We'll have fewer neurons responding than we're in the middle, but we're ignoring this edge effect. We're assuming that we're in a theta which is far from the edges. Okay?
One thing is you wrote the theta wave twice, like in the beginning.
Thanks.
And why is it okay to change to an integral?
Okay, because this is the definition of the integral. When delta theta is sufficiently sufficiently small, this is an approximation to the integral. Right? You evaluate the function at discrete positions, uniformly separated, and you divide by. It's like summing the areas under the function. Right? This is in general. The integral of a function, the definite integral of function f of x dx, say from 0 to a. From 0 to a is by definition it's the limit.
You can move the board.
Sure. This is by definition a limit of a set of calculations where you divide into finite delta x's, right? And you write this as, so it's the limit as delta x goes to 0 of some f of xi, times delta x various x, right? So when delta x is small, it's a good approximation.
Yeah, but then why do you change the I times delta theta to theta wave? Isn't that small enough?
Well, what the requirement here is that the delta x is small.
Yeah, but
so delta
I delta theta
So again, I delta theta is what I call here theta wave. And this integral, I could have written it by letting delta theta wave by summing up the values of this function over discrete positions, which are separated by a small number, and then divide by this number. So this is exactly what is written here. And my assumption is that delta theta is sufficiently small. Now, if we look back at this, it becomes clear when I say that delta theta is small, compared to what should it be small? It should be small compared to the scale over which this function changes. So if I would take a delta theta like this, it would not be a good approximation. But if my delta theta is small compared to the width of this reflective field, then I'm fine. Okay, let's take a break.
אני מבין את זה שכאילו חצי נוראים בינוניים, זה בסדר, אבל זה לא יהיה נכון. עדיין מעבר לאינטגרל נכון, זה חושב אינטגרל מ-0 עד 1000.
נכון, אבל אני שהתרומה של החלק שהוא מ-L והלאה ושל מ-0 והלאה, אני יכול להתעלם ממנה. זה יהיה נכון כל עוד אני רחוק מהגבולות האלה. אם אני מתקרב מאוד לגבולות האלה, מסדר גודל של הרחק טבעי, זה נכון.
אם הייתי רושם פה מ-0 עד 1000, מה זה היה?
לא, אז קודם כל היית מקבל תשובה שתלויה בתטא. כי למשל כשאתה במקרה הזה התטא גל היה הולך מ-L פחות או יותר עד 0, במקרה הזה הוא היה הולך ממינוס L עד חלקי 2 עד L חלקי 2, אז קודם כל היית מקבל תשובה שתלויה בתטא. אבל אני פשוט רוצה תשובה אחת. ואני אומר, לרוב הנוירונים, פרט לנוירונים שנמצאים בקצה, זה ממש לא משנה אם אני את הסכום הזה אוסיף עוד איזה נוירונים דמיוניים שממשיכים עד אינסוף. כי התרומה שלהם, ה-F דועך ל-0 מספיק מהר, ככה שאני יכול להזניח את התרומה שלהם. זה הרעיון. אוקיי? אז מה שאמרתי שבדוגמה הזאת קודם כל ה-Fisher information מתבדר בנקודה שבה התטא הולך לתטא כוכבית. למה הוא מתבדר? כי אני הנחתי שבניגוד לאיך שציירתי את זה כאן, שהנגזרת הולכת בצורה חלקה לאיזה, אני הנחתי שהיא לא הולכת בצורה חלקה. זאת אומרת, הנגזרת, כשאני מתקרב לנקודה הזאת, הנגזרת הולכת לאיזשהו קבוע, ויש לי את הנגזרת בריבוע, כי הערך של הפונקציה, אבל הערך של הפונקציה הוא 0, הולך שואף ל-0. אז מקבלים משהו שמתבדר. עכשיו אז קצת דיברתי על מה המשמעות של זה, אמרתי זה שזה מתבדר, זה לא אומר שבאמת הווריאנס של אסטימטור יהיה 0. ואני מדבר על זה עוד קצת בהמשך.
מה שראינו פה עם הפרסון,
כן.
אז בגלל זה כאילו אחר כך בניהול פרוסס של את הזמנים, אז אתה גם מכניס את המכפלה של הקצה, נכון? זה ממש כמו מה שאומרה בערך, נכון? אבל אני גם מבין יותר טוב קצת.
כן.
עכשיו כאילו לא היה אכפת לך רק יחד, בגלל רק לאיזה פרסוניה, חצי אינטרווליה, כמה?
בדיוק.
זה המצחיק.
נכון, עכשיו לריניול פרוסס זה לא אותו דבר לשאול מה ה-Fisher information במספר הספייקים.
זה יש לך הפרש בכל אחד, וכאילו פשוט ההפרשים האלה.
כן, ויש הבדל בין ה-Fisher information במספר הספייקים וה-Fisher information בתגמול של...
כן, אבל קיבלתי איזה גרף לשונות.
בסדר, אבל אפשר לשאול גם מה ה-Fisher information במספר הספייקים, זו שאלה לגיטימית. אפשר גם לשאול מה... אוקיי. אתה הסתכלת על שונות, אז שונות
כן, אבל זה קשורה לזה.
נכון.
אין מספיק גדול, אז אתה מגיע לפרמלה, זה בערך אפילו שלו. כאילו, לא? או שזה בכיוון.
אני חושב מה שנכון זה שגם בתהליך ריניול פרוסס, בתנאי מסוימים, בתנאי שההתפלגות של הזמנים היא לא מאוד מאוד רחבה, אז גם הריניול פרוסס, אפשר לחשוב עליו, אם אתה מסתכל עליו בזמן ארוך, אפשר לחשוב עליו כקומבינציה של דברים בלתי תלויים, איכותיים. ואז עדיין יש מקווים שיש Fisher information שהוא פרופורציונלי בזמן. אבל אפשר גם לחשוב על ריניול פרוסס שבהם זה לא ככה. אם יש...
גם הדיסטריביושן שלי זה סתם דוגמה לריניול פרוסס.
גם הדיסטריביושן זה דוגמה טובה, אבל אם יש ריניול פרוסס שהאינטרספייק אינטרוול שלו, הפרובביליטי אינטרוול דועך מאוד לאט, אלגבראית נגיד, לא אקספוננציאלית. ודועך מספיק לאט, אז יכול להיות מצב שככל שאתה מסתכל על זמנים יותר ארוכים, אז בכלל יש סיכוי שאתה תראה איזה אינטרספייק אינטרוול יותר ארוך, ולכן אין שום מצב שבו אני יכול לחשוב על האינטרוול הזה והאינטרוול הזה כבלתי תלויים. אפשר לחשוב על תהליכים כאלה. ואז בכלל הפישר אינפורמיישן לא פרופורציוני לזמן. אבל בדוגמאות שאתה הסתכלת, כשזה גם הדיסטריביושן, מדובר בגרף אקספוננציאלית, אז זה כן, על זמנים מספיק ארוכים, הספייקמן פה בלתי תלוי בספייקמן פה, ולכן הפישר אינפורמיישן הוא פרופורציוני לזמן. אולי גם עניתי לך, או צריך יותר ממה שרציתי לשאול.
לא, זה בסדר.
המשכתם בסדר או שזה 5 דקות?
לא, אין לנו הרבה זמן, עכשיו אתה יכול להתחיל. האמת שאנחנו...
אם זה התחיל.
סבבה.
שזה יקרה.
בעיה לשנות לך.
מיד אחרי יש לי איזה פגישה.
תשמעי, יכול להיות שתשכנע את החבר'ה שמעניין אותם, הם יגידו, וואלה, תבוא לשמוע. ויהיו חבר'ה שלא מעניין אותם. הוא יראה שזה לא שזה לא מעניין. בכל מקרה, תדברו להם על ויז'ן כל כך הרבה.
Okay. Just one clarification. Hope it will be a clarification about the change of limits of the integral. If we look at a particular theta, suppose that this is theta, okay? In principle, the theta i's go from the theta I goes always from 0 to L. So theta minus theta I will go from minus theta to L minus theta, right? So in principle, the integral, the summation of theta I, which we replace by integral, is over some finite range which depends on theta, which means that the Fisher information has some dependence on theta. But what does this dependence look like? As long as theta is far from the edges, the neurons here and here don't contribute anything anyway, because we assume that the receptive field decays sufficiently fast. So then I can imagine that there are additional neurons going all the way from minus infinity to infinity and include them, and this is essentially the approximation that I did here when I replaced the range of integration from minus infinity to infinity. It's not a valid approximation if theta is very close to the edges. Close to the edges over a range which is similar to the size of the receptive field, because then there are neurons only to the left, there are no neurons to the right.
But why you don't want J to be a theta? Usually it's...
No, it's, my point is just that if we have the situation of dense receptive fields for most values of theta, the Fisher information is independent of theta, which is a nice result. It's the same, and it makes sense because everything is almost translationally invariant.
So this is what you achieve by changing the...
Yes. Okay, so let's just write again the result. Okay, this part of the blackboard is a mess, so I'll erase it.
Why do you want to achieve it?
No, I don't. It's the result. What we got is that in this situation, but I know from the start that that's what I expect. I have. You know what, I could have said that instead of having neurons with receptive fields from 0 to L, I indeed have neurons with receptive fields from minus infinity to infinity, right? Everything then is translationally invariant. It doesn't matter what theta is, and so we better get a result which doesn't depend on theta, right?
I'm just saying, I feel fine with that if we get the Fisher information dependent on theta.
I understand. I understand, but in this situation where I imagine that the receptive fields have the same structure independent of theta, it makes sense that we should get a result which is independent of theta, and that's indeed what we got, up to edge effects. If the theta is close to the edges, it's not true anymore. Okay, so J, what we got is that J is equal to n over L integral from minus infinity to infinity f prime of theta square divided by f of theta d theta. And now I want to use this result in order to ask a certain question. The question that I want to ask is whether, if we were free to design a receptive field, would it be better to have narrow receptive fields or wide receptive fields? What do I mean by that? Imagine, so this is the game that we're playing. We have n neurons. Okay, so first of all, title. Conclusion of what from this will be a discussion on the question of wide or narrow receptive fields. And what do I mean by that? Imagine that we have n neurons with theta I going from 0 to L, theta going from 0 to L, and we're still in this situation of translationally invariant receptive fields, and f of theta, I will allow it to scale. So I write it as g of theta over alpha, g of theta over s. Okay. And what I mean by this is that I fix the structure of the receptive field, but I want to ask what is I allow stretching, either making it narrow or making it wide. So, for example, G might have a particular form that looks like this, but depending on my choice of f, f will either be like this or it will be more wide. Okay, so this is larger f, and this is smaller f. And note that in the rules of the game as I define them, I'm not varying the total firing rate so we have a population of these neurons with different positions. And note that for each neuron, what I keep fixed is the maximal firing rate, right? Which means that if I change S, I do change the total firing rate of my population. The total firing rate will be something like the integral of this function. So if I make the S larger, if I make the tuning curve wider, I will get more neurons per unit time from my whole population. But this is the rule of game. These are the rules of the game that I defined. What I maintain as fixed is the maximal firing rate. Motivation for thinking about this as a constraint is that we know that in particular brain areas, we have a typical maximal firing rate of neurons. So in the cortex, it's in the order of 10 hertz. More primary, more early sensory areas like the retina itself, maybe we can go up to 100 hertz. But there seems to be a limitation on the maximal firing rate that a neuron is allowed to fire. Nevertheless, it's not clear that this is this is the relevant optimization constraint on the neural system. Maybe there is an energy cost per spike, and we might want to constrain the total firing rate, which is not what we're doing here. But just this is an example. For the sake of the mathematical discussion that we're doing now, this is the game. We are allowed to change the width of the receptive field, and we want to ask what is the optimal receptive field, narrow or wide? Is it better to make S large or small?
What do you want to optimize?
So S. So what I'm allowed to change is S. And I want to ask, and what is the quantity that I want to optimize? The Fisher information. Okay? So we optimize the Fisher information. Okay, so let's write.
Why are you looking for the maximal Fisher information?
Because I want to design a code for theta, will give me the smallest variance of an estimator or the largest discriminability. Larger Fisher information means that the population response is more informative about this, allows me to do these discriminations more precisely. Okay, so let's write the Fisher information. We know what it is. We just need to plug in F this form for G. So J is equal to N over L. It's approximately equal because all of the approximations that we had up to now. integral from minus infinity to infinity d theta 1 over g of theta over s. Here we have d to d theta g of theta over s square d theta. But this is 1 over s g prime of theta over s, right? Just a chain rule for derivatives. Okay, and I will define here a variable x, which will be theta over s. So d theta is s dx. So we'll re-express everything using x. When theta goes from minus infinity to infinity, x also goes from minus infinity to infinity. So I have use theta prime.
No, okay, that's good.
Everything is okay?
Yeah.
Okay. N over L integral. So d theta I write as s s dx. Now I have here 1 over g of x. Here I have 1 over s square, right? This is this s square, g prime of x square. And so, is it okay that I'm writing here? No objections? Okay. So, this is, now you see here that I have here an s. Here I have 1 over s square. So overall I have 1 over s times n over L integral dx g prime of x square divided by g of x. And the integral is from minus infinity to infinity. Right? But everything written here is independent of s. So if I want to make the Fisher information as large as possible, what do I want to do? Make s as small as possible. So the conclusion is that optimal s, in principle, I would want to make the receptive fields narrow, infinitely narrow. Okay? So it's better to have narrow tuning curves, which kind of makes sense because a neuron which has a narrow tuning curve is more sensitive to theta than a neuron that has a wide tuning curve. Okay. Now, in principle, this calculation told us that we want to make s infinitesimally small. We want to make it 0. I claim that in reality, we will reach a problem when we try to make s smaller and smaller, because remember that our neurons are discrete. And all our calculation, this approximation, was under the assumption that delta theta is small compared to the width of the tuning curve. If we try to make the tuning curve very, very narrow, we will reach a situation where these are our neurons and we have a tuning curve like this, like this, like this, like this, and our whole calculation of the Fisher information is not correct. So in fact, narrow tuning curves, but it won't go to 0. It will be limited by delta theta. Okay, there's no point in making the tuning curve smaller than delta theta. The width of the tuning curve is smaller than delta theta. But in any case, we concluded that in this case, it's good to have narrow tuning curves. So in the representation of a one-dimensional variable using a translationally invariant receptive fields, we want to have narrow tuning curves. And now what I want to show you next is that surprisingly, for this optimization problem, the answer changes if we look at a representation of a multidimensional stimulus. If the stimulus is not one-dimensional, but of higher order, of higher dimension. For example, it could be position in 2 dimensions, and it's 2 dimensions. It could be position in 3 dimensions, and it's 3-dimensional variable. But in order to discuss this, we first need to discuss a multidimensional stimuli in the context of Fisher information. So I'll do it.
If you look only on the integral, the result wouldn't depend on s and all. If you evaluate this integral.
Which integral? This one?
No, down with the s.
So this, the s does not appear here, right?
Directly.
No, no, it does not appear here anywhere. This is the integral over x, g prime of x squared divided by g of x. So this, okay, we scaled it out, but so this is a kind of a dimensional analysis, what is called sometimes dimensional analysis. We find that the result is some power law of s, and we extract the power here. Okay, so keep in mind this result, because our goal is to repeat it in the context of a multidimensional stimulus, but now we need to take a short break from this discussion and consider multidimensional stimuli. And go back to the basic discussion of statistical measures like Fisher information. So imagine that now that theta is a vector, and it's an m-dimensional vector. And the first thing that I want to introduce, did you learn in עיבוד מידע ולמידה on Fisher information of a multidimensional variable? Yeah. Okay, contrasting responses from the audience. So I will define it. So the generalization is really simple. For a for a scalar variable, the Fisher information was a number, right? For an m-dimensional vector, the Fisher information is defined as a matrix. So it's an m by m matrix. And it's defined as follows: d to the theta alpha, d to the theta beta, log p of r given theta. Okay? Averaged over the distribution of r given theta. So you can see that if theta is one-dimensional, we go back to the definition that we had before. Then both alpha and beta are 1. There's just one index. The index, there's one entry, so it will be a 1 by 1 matrix, and this will be d to the theta square. The same, it turns out that it's also equal. I could have written also something similar to the other form of the Fisher information, which was d log p to the theta alpha, d log p to the theta beta. Okay, the same proof that shows that these expressions are the same in one dimension can be generalized to m dimensions. Okay, this is the definition of the Fisher information. And what is it useful for? It's useful because there is a generalization of the Kramer-Rao bound for multidimensional. Well, if alpha is equal to beta, this is a square. So there is a generalization of the Kramer-Rao bound. Okay, now what does the Kramer-Rao bound consider? In the Kramer-Rao bound, we consider an estimator, and we consider the variance of the estimator. So we define now the covariance matrix of an estimator as follows. For any given estimator, we look at the covariance matrix of the estimate. Okay. So this is a generalization of the variance of the error. And the Kramer-Rao bound tells us that for any unbiased estimator, E minus J minus to the minus 1 is, okay, I would want to say positive, but E is a matrix. And by J minus 1, I mean the inverse of the Fisher information matrix. So everything here is an M by M matrix. And the theorem states that if the estimator is unbiased, then this is a positive definite matrix. Okay. Now in the one-dimensional case, E is a number. This is J is a number, so the inverse is just 1 over that number. And we go back to the statement before that E is larger than 1 over J. But here it's a statement about matrices, and note that this is not the inverse. I mean, this is not a element by element inverse of J. This is the inverse of the matrix J. However,
There's always an inverse?
um,
Why do you assume?
so okay, so this is a good question. First of all, it's possible to prove that J is positive definite. Okay, the matrix J is positive definite. If J, there is, and it's also a symmetric matrix. So it can always be diagonalized. Now, what does it mean that it doesn't have an inverse? It doesn't have an inverse if there is an eigenvector with an eigenvalue which is vanishing. This is similar to the situation where the Fisher information in the one-dimensional case is 0. Okay, so you could have asked me also in the one-dimensional case, how do I know that J, 1 over J exists? Sometimes it doesn't. If J is equal to 0, then the inverse Fisher information is infinite, and then the variance is infinite. Okay, so this is kind of similar. Now, I do want to since this expression is somewhat obscure because we're discussing here the difference between two matrices, and one of them is the inverse of the Fisher information matrix, I do want to point out that there's a weaker conclusion coming from this expression. We might want to ask what is the variance of one element of the estimate of one of the elements of this theta. So theta is say a three-dimensional vector. I want to ask what is the variance of my estimate of the first coordinate, right? So this would be, that variance is E alpha alpha, right? It's the variance of theta alpha. Okay, so the variance of theta alpha is E alpha alpha, and I claim that this inequality or this relation implies that E alpha alpha is at least as large as the alpha alpha element of the inverse of the Fisher information matrix. Why is that true? It's true that because this is a positive definite matrix, and the diagonal elements of a positive definite matrix are always positive. Okay? So this is because it's a diagonal element of a positive definite matrix. It's positive definite because that's what the theorem tells us. And furthermore, because J itself is positive definite, it's possible to prove that this is at least as large as 1 over j alpha alpha. Okay, so again, this is the alpha alpha element of the inverse of the Fisher information matrix, but this, what is written here, is the inverse simply of j alpha alpha, and j alpha alpha is simply minus the second derivative with respect to alpha of log p of r. So basically, it tells us that for every element of the vector theta, we have an inequality which has the same structure as the one-dimensional inequality that we discussed before.
Why is the last?
Okay, so why is this true? Worthwhile to show it. It's not obvious, right? So let's. I will not do all the steps, but I will just sketch the proof. So the claim is that for any positive definite matrix, A, let's call it A just to remind us that this is a general statement. It doesn't have anything to do with Fisher information in particular. A minus 1 alpha alpha is at least as large as 1 over A alpha alpha. And sketch of proof. So I will consider, so the fact that A is positive, if A is positive definite, then A minus 1 is also positive definite. And the fact that A minus 1 is positive definite means that for any vector V, V transpose A minus 1 V is larger, at least equal to 0 for any choice of the vector V. And I will choose a very specific form of V. Why? Because it will yield the conclusion that I want. So I will take a vector that I will call U alpha. And U alpha is a vector that has zeros everywhere except for the alpha element. Okay, so if it's a three-dimensional, okay, this is an n-dimensional vector. I assume m-dimensional vector. M is the size of the matrix. I take a vector which has zeros except for 1 in position alpha. Okay, but I multiply this vector by the following matrix: the identity matrix plus C times A. And C is a scalar, okay, that I can choose whatever way that I want. And what this statement tells me is that for any value of C, this must be positive. Okay? So now, if I write V transpose A minus 1 V, it's not a lot of work to show, and I urge you to do it, even if we don't put it in the exercise, the home exercise. It's not a lot of work to show that with a particular choice of V that I made, this thing is a quadratic function of C, which has the following form. It's C square A alpha alpha plus 2 times C plus A minus 1, the alpha element of A minus 1. Okay? And I will finish my sketch of the proof here. So so this is just a construct, and what we know is that for any value of C, this thing must be positive. Now this is a quadratic function of C. In general, how does a quadratic function look like? It's a parabola, right? So if this parabola is positive everywhere, then it's in particular positive at its minimum. So this value must be larger than 0. And if you write down the expression for what is the minimum of this function, then plug in to see what is the value of this function at its minimum, which is this value, you will conclude that A, what we need, that A minus 1 alpha alpha is at least as large as 1 over A alpha alpha. These are basically the numbers that appear here. So this is and it turns out that that's the result that you get. Okay, this was just a very mathematical interlude, but I think it's actually amusing to see how you prove this property. And it's general. I mean, it doesn't have anything to do in particular with Fisher information. It's true for any positive definite matrix. Okay. Now let's get back to neural coding. So now I want to discuss the Fisher information for a population of neurons. Neurons in the multidimensional case. And I will not prove, I will not rederive the results, although, I mean, in principle, one has to do it. We derive the Fisher information for Poisson. Okay, let's put in here Poisson. We derive the Fisher information for Poisson neurons that depend on one parameter. It's not difficult to generalize this to the case where the parameter is a vector. And it turns out that the Fisher information, the alpha beta element of the Fisher information matrix is sum over all the neurons, dfi to d theta alpha, dfi to d theta beta, divided by fi, where I assume that that the firing rate of neuron I fires with rate fi of theta. Theta is a vector now. So you see that if it's in the one-dimensional case, we get back to the result that we had before, df to the alpha square divided by f. But the Fisher information matrix looks like this, and I will rewrite it just in a shorthand notation like this. So when I write d alpha f, I mean nothing but just a shorthand notation for df to the alpha. Okay, so that's the Fisher information matrix. And now I want to go back to the discussion of narrow versus wide tuning curves. And I will assume that we have d dimensions. So d can be 1 if it's one dimension, 2, 3, and so on. We'll do it generally. Okay, so J alpha beta is equal to, okay, so we consider again the situation where we have translationally invariant tuning curves that tile all the space of possible values of our stimulus. But our stimulus now is d-dimensional. So the relationship that we had in one dimension was that L over delta theta is equal to n, the number of neurons, but in d dimensions, L over theta, delta theta to the power d is equal to n. Right? Imagine that you have a two-dimensional theta. So this is 0, this is 0, this is L by L box, and we have receptive fields that need to tile the whole space. So the number of neurons is going to be L over delta theta to the power 2. This will be the area of this square. Okay, so in general, in d dimensions, delta theta is going to be to the power d is going to be equal to L to the d over n. And now I'm again skipping some steps, but if we're dealing with a case, so I should write this translationally. Invariant dense receptive fields, and we repeat everything that I did for the one-dimensional case. Turns out that what we get is that J alpha beta is equal to n over L to the power d, integral d-dimensional integral over theta, d alpha f, d beta f divided by f. And now if I continue and play the game that I played before, and I assume that my receptive field so remember fi of theta, just this I should have written even earlier on. The fi of theta we assume is f of theta minus theta I, and this is a function of a d-dimensional vector. And now I assume that this function f of theta, I'm allowed to scale it such that it's wide or narrow while maintaining the maximum firing rate fixed. So I write it as theta, g of theta over f, the same thing that I did before. Turns out that if I repeat everything that I did before in the one-dimensional case, and this I will leave it for you to do. What I get is that J alpha beta, instead of being proportional to 1 over S, it's proportional to S to the power D minus 2. Okay? I have to do a little bit of work to do this, to do the very similar things as what we did before, but because it's d-dimensional, there are some slight differences, and this is what you get. J alpha beta is proportional to S to the power D minus 2. Now just as a check, if we plug in D equals 1, we get 1 over S, which is what we got before, right? Okay, so when D is equal to 1, J is larger for smaller S, so we want to have narrow tuning curve. And it's limited by delta theta. This is what we discussed already. But now you see that if D is larger than 2, then we have here a positive power of S, right? So it's actually better to make S large. So if D, the dimensionality is larger than 2, we want to have wide tuning curves.
For D equals 2, it doesn't matter.
And yes, exactly. For D equals 2, it doesn't matter. We'll get the same Fisher information regardless of our choice of S. In reality, it's not precisely true, and this is because of edge effects. So I completely neglected in my discussion the effects of the edges, right? all my integrals from minus infinity to infinity. The edge effects do matter, and then they